This presentation is about HFSS analysis of planar archimedean spiral at an operating frequency of 4 GHz to 10 GHz. Planar archimedean spiral is a flat spiral with constant spacing between its turns, commonly used in spiral antennas. Its geometry follows the relation R equals to A plus B theta, giving it frequency independent behavior. Planar Archimedean spiral operates on a frequency-independent principle, where radiation is governed by geometry rather than resonance. When excited, a traveling wave moves along the spiral, and radiation occurs from an active region where the spiral circumference matches the wavelength, enabling wideband operation. Physically, the current flows smoothly along the arms, producing a stable broadside pattern with circular polarization and nearly constant input impedance over a wide frequency range. This Smith chart shows how the input impedance of the planar Archimedean spiral varies with frequency. The red curve represents the S11 response from the frequency sweep, indicating changes in both resistive and reactive components. Since most of the curve stays close to the center of the chart, the antenna is well matched over a wide bandwidth. This smooth impedance variation confirms the frequency independent and wideband nature of the spiral antenna. This plot shows how the voltage standing wave ratio of the planar Archimedean spiral varies from 4 to 10 GHz. VSRW indicates how well the antenna is matched to the transmission line, where lower values mean better matching. The graph shows a smooth and gradual increase with frequency, without any sharp peaks. This confirms stable impedance behavior and wideband operation of the spiral antenna. This graph shows the return loss of the antenna from 4 to 10 GHz, and the negative values mean most of the power is actually entering the antenna. You can see a dip around 8 GHz, which indicates better impedance matching and lower reflection at the frequency. The bandwidth is evaluated using the -6 dB return loss criteria, which is suitable for non-resonant spiral antennas. From the return loss graph, the antenna operates effectively from about 7 GHz to 9 GHz, giving a bandwidth of 2 GHz. The center frequency is 8 GHz, resulting in a fractional bandwidth of 25%, which clearly indicates broadband performance. This polar plot shows the directivity pattern of the planar Archimedean spiral antenna at 4 GHz for different angles. The overlapping curves indicate that the radiation pattern remains stable and consistent across multiple planes. We observe a broad main lobe, which implies wide angular coverage. Overall, the smooth and uniform pattern confirms minimal distortion and supports the antenna's suitability for wideband applications.
Radiation pattern. The 3D gain pattern shows the distribution of antenna radiation in space, while the polar plot represents gain variation with angle. Both plots indicate maximum radiation along the main lobe. This confirms the directional behavior of the antenna. Realized gain at 4 GHz. The realized gain plot at 4 GHz illustrates how antenna gain varies with angle. A clear main lobe indicates efficient radiation in the desired direction. Side lobes represent reduced radiation in other directions. Realized gain at 10 GHz shows the antenna's radiation performance at higher frequency. The main lobe indicates maximum gain direction. Additional side lobes appear due to frequency effects. Antenna's efficiency is calculated from the ratio of realized gain to directivity. The obtained values indicate that most of the input power is effectively radiated. This confirms low radiation losses. The effective area represents the antenna's ability to receive power. It is calculated using wavelength and gain. The effective area decreases with increasing frequency, which matches theoretical behavior. The polarization ratio plot shows the variation of circular polarization with respect to angle. A strong peak indicates dominant circular polarization in the main radiation direction. This confirms good polarization purity of antenna. Trade-offs. The antenna achieves very wide bandwidth, but this results in relatively low realized gain. Its compact size reduces radiation efficiency, especially at lower frequencies. Although circular polarization is supported, axial ratio performance degrades near the band edges. The planar structure causes some back radiation, and the wide beamwidth leads to low directivity, requiring a complex broadband feed design. Applications: due to its wide bandwidth, the antenna is suitable for ultra wideband communication systems. It can be used in radar and electronic warfare applications where wide frequency coverage is required. The antenna is also useful for direction finding, spectrum monitoring, and EMI or EMG measurements. Additionally, it can be applied in satellite communication and wideband sensing and imaging systems.